Hey, welcome back. This is Trig 4.7, talking about inverse trig functions. So if you took pre-calc, you should be a little bit familiar with these guys. So let's take a look. So first, to be invertible, you have to pass what's called the horizontal line test. You may remember the vertical line test. So for a function, or for a relation to be a function, it had to pass the vertical line test. Okay. For a function to be invertible, then it has to pass on top of that the horizontal line test. So invertible functions need to be one-to-one, is what it comes down to. So again, what does that mean sort of visually? Let's take a look at some common functions here. So this is y equals x squared. It's clearly a function because it passes a vertical line test. Any vertical line only hits the graph in one place, but it's not invertible, and it's because if you graph a horizontal line there, it will impact the graph in two places. So it is a function, but unfortunately it's not one-to-one, so it's not invertible. Okay. So what kind of objects have we dealt with that are one-to-one? Well, the exponential function y equals e to the x. Okay. So you can see any horizontal line you draw is only going to hit the graph in one place. Okay. So maybe here's two examples. So this is one-to-one, and it is invertible. And if you took pre-calculus, you know what its inverse is. It's just the natural log of x. Okay. Here in pre-calc, though, we're dealing with the trig function. So let's look at trig function. So, for instance, sine x, like this, and that just keeps on going on and on forever in both directions. Okay. So is this one-to-one? And no. Clearly, right? So if you draw a horizontal line here, it's going to hit it in an infinite number of places, so there's no way, right? A horizontal line can only hit the graph in at most one place, and so this guy is not one-to-one, and therefore not invertible. Okay, so in pre-calc, what was the solution? So the solution for y equals x squared was to kind of restrict the domain and force it to be one-to-one. So you probably saw y equals x squared being drawn out like that, and then to get its inverse function, you just rotate it about the line y equals x, and you end up with this character, which turns out to be the square root of x. Okay. We're going to do the same sort of thing here with the trig functions. Over here on the right, but the restricted domain is maybe not as obvious because there's a bunch of different ways you can restrict the domain and make it one-to-one. What we'll give you is kind of the traditional way of restricting the domain, and maybe in your applications later on in life you'll see other kind of domains, but this is the traditional way of doing things. So first we'll look at the inverse sine function. And let me remind you of the graph. So going by pi over 2's, so 2 pi over 2, which is just pi, 3 pi over 2, 4 pi over 2, which of course is 2 pi. In the other direction, negative pi over 2, we'll just go over to negative pi. Okay. So the picture then, of course, the amplitude is 1, so it's going to go up and down to 1. And then it looks like this. Maybe I should just get the key points there so it's a little easier on me to graph this thing. And then it's going to go down and then back up. Okay, so there's a little more than one period, a period and a half. And of course, it goes on forever. Okay, so how are we going to restrict the domain in order to make this guy invertible? I'll put it in red. We're just going to go from negative pi over 2 to pi over 2. And you see that object, then that thing in red that I just drew, will pass the horizontal line test. Okay, so this is, the graph of sine x, but we're going to limit its domain to make it invertible. So I'm going to go from negative pi over 2, which is like negative 1.5-ish, to pi over 2. And then the range is going to be basically based off the amplitude, going from negative 1 to 1. Okay. To get the picture of the graph, you could just kind of rotate it about the line y equals x. So right now it kind of looks like this, that one wedge that we have. And then we want to rotate it about the line y equals x, which is that blue line I just drew. And so in the end, I guess I'll put it in yellow, our sine inverse graph will be this yellow graph. Okay, so let me redraw the sine inverse graph then down here. So now on the x-axis, its domain will go from negative 1 to 1, and then its range will be negative pi over 2, which is around 1.5, negative 1.5 to positive pi over 2. And it'll look like this. Okay, so this is y equals sine inverse of x, and we use that exponent as just purely as notation. Sine to the negative 1 of x is not equal to the sine x, not equal to sine x to the negative 1. Okay, sine x to the negative 1 is 1 over sine x. The sine inverse is not 1 over sine x. Okay. So to kind of keep us from thinking that, and I mean, think about what 1 over sine x is. That's just the cosecant function, and clearly this is not the cosecant graph, right? So anyways, one way to get around that issue, you'll see sometimes, is they'll call sine inverse arcsine. I don't know why that thing keeps popping up on me. Okay. So instead of sine inverse x, we'll call it arcsine of x. Okay, the domain and range then of this thing will just be kind of the reverse of the original domain and range. So now the domain is going from negative 1 to 1 on the x-axis, and the range will go from negative pi over 2 to positive pi over 2, which I just see now I miswrote negative pi over 2 on top and bottom. Whoops, sorry about that. Okay, let's look at some exercises from the book. So we'll start with problem 1, and they want to know what is sine inverse of 1/2. So what does this come down to? Let me make sure I'm recording. This stupid thing keeps popping up. I'm like, what is that? This thing. I have no idea what this is, and I just want to get rid of it forever. No. Okay. Am I recording? Yeah. It's always something, I hope that thing stops. I don't know what it is. Anyways, yeah. So what is this asking? It's basically, you kind of think of it in the reverse way. If you remember when we first defined logarithms, you have to kind of think of them in reverse. So like the log base 3 of 9, what is that? So you'd have to think, well, 3 to what power equals 9? And then that would tell you that x must equal 2. So log base 3 of 9 is 2, right? So you kind of have to, in the beginning, think of it that way. So here we have sine inverse of 1/2. So I want to know the sine of what angle theta is equal to 1/2. Okay, that's an equivalent way of stating this question here. When I figure this out, I think in terms of this unit circle on our new range. Okay, so the output of sine inverse has to be in between negative pi over 2 to pi over 2. Okay, there's two angles in there that would give me 1/2. One's negative, one's positive. I need positive 1/2. So the angle I need is in the first quadrant. Right, so the angles in this first quadrant will give you positive outputs. The angle in this fourth quadrant will give you negative outputs. So if your output is positive 1/2, you need the angle in the first quadrant, the reference angle that gives you 1/2, and that reference angle is pi over 6. You just have to have kind of your chart memorized. And here we go. It's pi over 6. Yeah. Office hours. All these pop-ups, I'm sorry. Okay, so that's the answer for that. Let's look at another one. Here's problem 6. We're trying to figure out sine inverse of negative radical 3 over 2. Okay, so you're thinking to yourself, the sine of what angle is equal to negative radical 3 over 2? Well, the reference angle for radical 3 over 2 is pi over 3, right? So we want some variation of pi over 3 in our answer. And looking at the unit circle, because this output is negative, our answer, our angle is going to be in that 4th quadrant. So not positive pi over 3, which would give you radical 3 over 2, but rather negative pi over 3 down here. So your answers here have to be in this range. That's why I'm drawing that little unit circle to kind of remind me of what the range is. So I'm always going from negative pi over 2 to positive pi over 2. And your answer has to be in that interval. Okay, so in this case, we're going to want the negative pi over 3 as our answer. Okay, we're going to play the same game with cosine now. So let's take a look at inverse cosine. And we're going to have to restrict its domain again because obviously it's going to fail. Otherwise, it will fail the horizontal line test. So let's get this drawn out. Let's get some tick marks in both directions. So pi over 2, pi, 3 pi over 2, 4 pi over 2, which is 2 pi, negative pi over 2, negative 2 pi over 2, which is just negative pi, and get some amplitude of negative 1 to 1. Let's get our main points for cosine, our key points. And, did I draw that wrong? Sometimes I mix them up. No, I think I'm good. Okay, so graph will look like this. Sort of kind of butchering it there. Okay, so the spiel is if we just restricted it on the same domain, which would be convenient and easy to memorize, the problem is if you go from negative pi over 2 to pi over 2, do you see the issue? It's not invertible anymore because it will fail the horizontal line test. So you'll have a horizontal line going through this hump and basically hitting it twice, and so it won't be invertible. So what we need to do is kind of shift our domain to make this work, and the domain we use traditionally is going from 0 to pi. Okay, the range then will be basically based off the amplitude, negative 1 to 1, and it's a little harder to get the inverse of it because, and I'll put it in, the thing we want to kind of rotate right here. This is the cosine function on this restricted domain. I just drew in red. We want to rotate that about the line y equals x, and that's a little bit more difficult, right? So if I want to rotate it about that line, it's a little harder. You can kind of finagle it, so it's going to, hit at 1, and then kind of zip over and go like that. So you can see they're mirror images of each other, but not really. It's a little difficult to do that guy. Let me just draw it over here. And it kind of looks like it's kind of like a weird kind of cubic type thing. Anyways, here are its domain points. So again, here I'm drawing cosine inverse, which again, that negative 1 exponent doesn't mean an exponent. It's just notation for cosine inverse, right? So if you want to, you can write arc cosine, but its domain now will go from negative 1 to 1, which is what I was plotting there, negative 1 to 1. And then its range will now be the domain of the original function, which is 0 to pi. Okay, so I'm going to go by pi over 2 on the x-axis and end up at pi up here, pi over 2, and the curve looks like this. So it's kind of bowl-shaped down and then bowl-shaped up, which we call concave down, concave up. Okay, and there it is in all of its glory. Okay, so you'll be called upon to do the same kind of questions as before. Let's take a look at some of those. So number 7, we have cosine inverse of root 3 over 2. And again, you want to keep in mind kind of the unit circle and the sign of cosine in that part of the unit circle. So now our outputs need to be from 0 to pi. Excuse me. And cosine is positive in this quadrant and negative in this quadrant. So again, I'm looking for the angle theta such that the cosine of that angle is equal to positive root 3 over 2. So it has to be in the first quadrant. And the reference angle that gives root 3 over 2 is just pi over 6. Okay, so your answer here will be pi over 6. Let's look at another. So number 9, cosine inverse of negative root 2 over 2. Okay, so again, thinking about the unit circle here and the range of cosine, we know it has to be now in the second quadrant because we're dealing with a negative output for cosine theta. Okay, so we're asking ourselves what angle such that when I take the cosine of it equals negative root 2 over 2. So the reference angle would be pi over 4, right? But we don't want the one in the positive quadrant. We want the one that's giving us a negative output. So you want this angle in the second quadrant, which is 1 pi over 4, 2 pi over 4, 3 pi over 4. Okay, so our answer, 3 pi over 4. Okay, let's look at the inverse tangent function now. So section 3, inverse tan. And again, you're going to see this issue with, it not being invertible. So anyways, we always put the tangent function from negative pi over 2 to pi over 2. So pi and then 3 pi over 2. We'll just put 2 periods in. Okay, and then kind of get its graph. Kind of looks like this. And then it repeats to the left and to the right. But here's 2 periods. And you can see, again, it's not going to pass the horizontal line test. So what we're going to do this time is restrict it in kind of the same way that we restrict the sine function. We're going to restrict it between negative pi over 2 and pi over 2, but we can't kind of include those endpoints because of the asymptotes. So if you compare and contrast this with the sine function, you'll note the sine function's domain, we include those endpoints, but now we don't. Okay, so then the range will be, negative infinity to infinity. And so the portion that we're using that we've restricted ourselves to is this blue graph. Okay? And we want to rotate it about the line y equals x. So it's going to be rotated about this line. And the result of that rotation then is going to kind of be like this. Okay? And the asymptotes will kind of rotate 90 degrees as well. So you're going to end up with some asymptotes here and an asymptote down here at pi over 2 and negative pi over 2. Okay, so let me redraw it in all of its glory. The inverse tan function. So it has asymptotes on the y-axis now. Let me draw those in. And then it has this kind of cube root looking behavior. It's not a cube root though. Okay, so this is tan inverse, or arctan, if you want to get around that issue with the exponent. That's not really an exponent, it's just notation. The domain this time is the range from the previous function, so negative pi to pi, and sorry, negative infinity to infinity, and then the range will be negative pi over 2 to pi over 2. Okay. Of course, they're going to ask you for the same type of problems. You know, find tan inverse of this thingamajig. So we want to know the first one, tan inverse of root 3 over 3. Okay. So I'm going to draw my unit circle, and it's just like the unit circle, the portion of the unit circle for the sine inverse, except I'm drawing open balls there at the negative pi over 2 angle and the pi over 2. Okay. All right, so I need my output to be in that range. And the reference angle for, and of course this is the positive, this will be the negative, so ultimately I'm looking for the angle such that tan of that angle is equal to root 3 over 3. Okay, so that will be the pi over 6 is your reference angle, and just make sure, yeah, we need the positive version, so the answer is just pi over 6. It would either be pi over 6 or negative pi over 6. It would be negative pi over 6 if we were looking for tan inverse of negative root 3 over 3, right? Okay, let's look at another one. Oh, cool, and then this one is the negative version. So negative root 3 over 3. So again, you know, you're thinking in this range from negative pi over 2 to pi over 2. I'm trying to find the angle such that the tan of that angle is equal to negative root 3 over 3. This time the reference angle, of course, is pi over 6, but we want the output to be negative, so I need to use negative pi over 6. Okay, so tan inverse of negative root 3 over 3 is negative pi over 6. Okay, another way of thinking of this is I kind of you know, I kind of submit it as a conceptual thing. Another way of kind of getting your answer is to take the tan on both sides. These are called doing the cancellation equations, which you might remember from pre-calc. So if you have tan inverse of some angle, right, and you can, and you're saying it equals to some other so tan inverse wouldn't actually be an angle in here. That would be some number. The ratio, you can think of it as a ratio of sides of a right triangle. So I'll just put A, right? And then the output would be some angle theta. So the equivalent question you could kind of form by taking the tangent of both sides. So the tan of tan inverse of A equals the tan of theta. And then this question that I'm always asking here, the related kind of inverse question is sitting there, right? So you say to yourself, well, tan of tan inverse, these kind of cancel each other. You're just left with A, and you have tan theta equals A. Okay, so I mean, that's kind of what I did up here. So look, if you take tan inverse of root 3 over 3, and on the other side you have pi over 6, you could take, whoops, we didn't know we had pi over 6 on the other side, right? So we just put some angle there. If you take tan on both sides, you get this expression that I was sort of just giving to you, right? So over here the tans cancel and you get root 3 over 3. On the other side you have the tan of theta. Okay. It's not so easy when you're going in the other direction. So if you take like sine inverse of sine, you have to be a little more careful. And I think this section in the book is called the Compositional Functions. And I suggest kind of doing it in 2 steps. So we'll just dive into where the questions are. First, they're asking a sine inverse of sine of pi over 3. Okay, so again, I suggest you kind of just do 1 step at a time, move from the inside out, right? So on the inside, the sine of pi over 3, we hopefully have memorized, is root 3 over 2. So I'm looking for the sine inverse of root 3 over 2. Okay, and then you go to your unit circle. I'm in between negative pi over 2 and pi over 2. The reference angle that gives me root 3 over 2 is pi over 3. So the answer is pi over 3. What you want to be careful of is to not accidentally think that the sine and the inverse sine always cancel and just leave you with the pi over 3, right? And an example here, and this will be your video quiz question, okay? So this will be problem 35, and you just basically just copy it down exactly how I do it, and that'll be basically the easiest quiz in the universe, right? Okay, so this is my video quiz question, problem 35. What is the sine inverse of sine of 5 pi over 6? Okay, so I'm going to start in the middle, on the inside there, and figure out the sine of 5 pi over 6. Okay, so where is that on the unit circle? Here's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. Okay, sine is positive in that quadrant. It's also positive here. The reference angle is, the sine of 5.5, the reference angle is pi over 6, and sine of pi over 6 is is 1/2. So when we're in the second quadrant, it's still positive, so it's still 1/2. Okay. Now I need to go into our sine inverses range. And I'm going to be in that first quadrant, so I need the angle such that if I take sine of that angle, it equals 1/2. Right? So that angle will be pi over 6. And so my answer is actually not 5 pi over 6, but pi over 6. Okay, so you got to be careful. It's not like these guys are totally will cancel out. There's some weirdness because of the way we've defined the domain. Okay. Let's look at another one. Here's 36. We have the cosine inverse of the cosine of 4 pi over 3. Okay. Okay. So again, I advise you to work inside out. So I have cosine inverse of 4 pi over 3. Where is that? It's 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Cosine is negative there. The reference angle is pi over 3. Cosine of pi over 3 is 1/2. Cosine is negative in that quadrant, so we're looking at negative 1/2. And then I gotta worry about the cosine inverses range from 0 to pi. And the angle, the quadrant where it's negative is going to be that second quadrant. So I need an angle, the reference angle for 1/2 would be, what, pi over 3. So I need the pi over 3 type angle that's in the second quadrant. That'll be, here's 1 pi over 3, 2 pi over 3 is what I need. So it's a little awkward at first. It's kind of like rubbing your head and patting your stomach at the same time, or vice versa. It's, yeah, it takes some getting used to, and hopefully you can appreciate. This takes some practice. This probably isn't something, if you were born in the woods and you're one of those feral children or something, that you would figure out on your own, right? No, this is something you have to practice and become familiar with, do flashcards, something like that. However you learned your multiplication tables, think back to that. How can I kind of learn this new material? Okay. So tan inverse, let's look at another one of tan of 3 pi over 4. Again, it's this issue. The answer is not going to be 3 pi over 4 in all probability. So one thing at a time. Where is 3 pi over 4? 1, 2, 3 pi over 4. Tangent is negative in that quadrant. Tan of pi over 4 is root 2 over 2. So the negative version is negative root 2 over 2. Okay, and then we think about the range of tan inverse. We need something in between negative pi over 2 and pi over 2. Tan is negative, so it has to be in this fourth quadrant. And going downwards, we will have negative pi over 4. Yeah. Okay. Every once in a while, it won't work. Okay, so let's look at 46. We have cosine inverse of 3 pi. So what's the issue here, right? Well, you can't, 3 pi is not in the domain of cosine inverse. Again, what's the domain of cosine inverse? That's 0 to pi. Right? 3 pi is not in there, so we would say it's undefined. And there's an option for that in my math lab. So that's always a possibility. Okay, let's look at one now where we're not dealing with the same sort of trig function, right? So up here, all we've been doing is like sine inverse of sine, cosine inverse of cosine. But what happens when we do something like sine of tan inverse or something like that? I think the book calls these mixed composites. And we'll take a look. Okay. So what I recommend doing is kind of drawing a triangle in the appropriate quadrant based on your knowledge of tan is what, opposite over adjacent. So the input of tan inverse is the ratio of sides of a right triangle. Like the output is usually the ratio of sides of a right triangle. But when you're doing it the inverse, the input is the ratio of sides of a right triangle. So in this case, and you want to put this triangle in the appropriate quadrants based off of the inverse tan function. So you know it has to be in one of these two quadrants. Okay, because it's positive, you know it has to be in the first quadrant. What you're going to do is draw a little triangle in there, a right triangle. Okay, and then 7 over 24, what is that? It's opposite over adjacent. Okay, so you'll build this right triangle. I don't have enough room for my numbers, so I'm just going to kind of extract it and put it over here. The opposite angle for this guy is going to be 7, and then the adjacent is the 24. So 7 is kind of like the y coordinate, and 24 is the x coordinate. So this side, again, is 24. This side right here is smushing it in is 7. So sine of this triangle is opposite over hypotenuse. So I need that hypotenuse, and of course you could get that via the Pythagorean Theorem, right? So you just have 7 squared plus 24 squared equals c squared, and then solve for c. So that would be 7 squared plus 24 squared. And you put that in your calculator, it's 25. Okay. So that hypotenuse is 25, so sine of this angle in this triangle is going to be opposite, which is 7, all over hypotenuse, which is 25. Okay. So you take a look at the inverse function, you draw your appropriate kind of region in this circle. It's not a unit circle now. And then you put the triangle in the appropriate quadrant and kind of figure out the sides, and then use your knowledge of like opposite over hypotenuse and that stuff to figure out your answer. So let's try another one. We'll try 2 more. Okay. So this is tan of sine inverse of -3/5. Okay. Okay. So the sine function is from -pi/2 to the pi/2. The input here, and of course this is ratio of sides of a right triangle, so it's going to be opposite over hypotenuse. That thing is negative, so it's got to be in this fourth quadrant down here. So let me draw my triangle, and here's my angle that I'm working with. It's a right triangle. The opposite side from that angle then is -3. Okay, and you think of this point as an xy coordinate, right? So for this side to be any value, it has to be negative because you're obviously going down on the y-axis by 3. Okay. Then the hypotenuse is always going to be positive. Okay, so this is 5, -3. And whoops, sorry, I lied to you. We have the y-coordinate. I need the x-coordinate, but you can get the x-coordinate from the 3 sides of the right triangle, right? So let me just rewrite the triangle so it's a little bigger for us to see. This is -3, 5. I need that third side, right? And if you do enough of these triangles, you'll see it's a 3, 4, 5 right triangle. They're called Pythagorean triples. So there's all these triples of numbers that represent integer valued right triangles. So all the sides are integers, they're counting numbers. And 3, 4, 5 is one of those special kinds of triangles. There's a class called number theory. If you keep on taking math, you could beat that to death playing around in number theory and stuff. Anyways, where are we? What is the x-coordinates? 4. Okay, so that position is 4, -3. And then the tan of this angle, as ratio of sides of a right triangle, we know that tan of theta is equal to what? Opposite over adjacent. So it's actually -3 over 4. One more. So let's look at 58. And we're looking at tan of cosine inverse of -1/4. Okay. So cosine now goes from 0 to pi. The input here is negative, so it's telling you it must be in the second quadrant. And then the cosine, remember, is adjacent over hypotenuse. So let's draw our triangle and figure out the sides. Okay, there's our triangle. So the adjacent side must be the -1. So -1, and then the hypotenuse is 4. Okay. And then the opposite side, again, we're going to have to do a Pythagorean Theorem type thing. We have -1 squared plus b squared equals 4 squared. Okay, we got to solve for b. So b squared will equal 4 squared is 16 minus -1 squared is just 1. So 16 minus 1. So b will be the square root of 16 minus 1, or square root 15. So this side over here, square root 15. So the tan of that triangle, opposite over adjacent, is going to be root 15 all over -1. So negative root 15. Okay. One application of this won't come up until you're way down the trail in Calculus 2. And what we'll be wanting to do is to take these trigonometric functions and turn them into rational functions or algebraic expressions. Okay. So there's kind of different classes of functions. And one class is called algebraic, and that includes like ratios of functions, square roots of functions, big long polynomials, and then there's other kind of classifications of functions, and the trig functions are considered what they call transcendental. So ideally we want to convert everything into algebraic functions because this will become a little easier to deal with, and so later on the road we'll want to do this kind of thing. So you saw it here first, folks. So simplifying it, it's going to be kind of unmotivated right now, but later on it becomes kind of important. So what's the deal? We're going to take an expression like sine of tan inverse of x and rewrite it just in terms of maybe some fractions, some variables, some square roots, no trig functions. Okay. So here we go. The first thing I'm going to do is kind of reimagine x as a ratio. Okay, so x is the same as x over 1, and we know tan, the input of tan inverse in this case will be opposite over adjacent. Okay, so we use this information to construct a right triangle. We're not worried about negatives or anything like that, like which quadrant is it in. We kind of just brush that under the carpet, so to speak, for now. Then opposite from this angle is this side, adjacent is this side, and then for sine we need opposite over hypotenuse. So I need to figure out the hypotenuse side, and I use the Pythagorean Theorem again. So the x squared plus 1 squared equals hypotenuse squared, which I call c. So I have c squared equals x squared plus 1, square root on both sides, and you get c, and we just take the positive square root, x squared plus 1. Okay, so the third side we can build as x squared plus 1. And then you just take the sine of this angle. So the sine, again, is opposite over hypotenuse. So we can reduce this ugly-looking transcendental thing that at this point we barely know how to deal with, and turn it into what's called an algebraic expression. Okay, so square roots, division symbols, variables only, plus signs, minus signs. Okay, so it turns it from something scary into something a little less intimidating. Let's look at another. We have secant cosine inverse of 1 over x. Okay. And again, we build this right triangle based on the idea that we can re-envision this ratio as a ratio of sides of a right triangle. So cosine is adjacent over hypotenuse. Very important to memorize all that stuff from earlier sections. Let's draw a right triangle, and we have theta here. Adjacent is 1, hypotenuse is x, so I need the third side. 1 squared plus, we'll call that third side b squared, equals x squared. B squared is x squared minus 1. And then b is apparently square root of x squared minus 1. So our third side, draw it in here, x squared minus 1. And then the secant of this angle is going to be hypotenuse over adjacent. Okay? So hypotenuse over adjacent, you kind of see here they're just reciprocals. It's just kind of done a reciprocal of the 1 over x, turned it into x over 1. In general, I wouldn't, look for patterns like that here. Just use your triangle and go from there. So let's see what we have in WebAssign. I'm looking for the right browser because not all my browsers work for WebAssign. We're talking about 4.7. Let's go up to the homework. Okay, homework 4.7. I kind of browsed through the problems. I didn't really get carried away with doing any of them. Let's take a look at it. So there's just some simple questions. Use your calculator to find the expression. So in your calculator, probably by the tan button, you should have a tan inverse right above it. Okay, so on the TI-30X2S, that's the case. So tan, and then above it you have tan inverse. Make sure you are in, I think we need to be in radians to deal with this. So let me just be sure. Tan inverse negative 12, right? So let's turn on my computer. Mode radians. Clear. And we're going tan inverse. I mean, it doesn't really say, but tan inverse of negative 12. I'm getting negative 1.487 something. So 2 decimals, negative 1.49. Okay, so yeah, your mode needs to be radians. At least for these. Let's see what else they got for you. Cosine, find the exact value. Let's see. So the output of cosine inverse is going to be. This is one where it just cancels. So you just have negative 0.9 in here. Let's check the answer. This would just be pi over 5. So when oh, wait a second. This is one where you have to be careful. So when cosine is on when the inverse portion is on the inside, you can just cancel. But when the inverse is on the outside, then that's one you have to be careful about. This one, they want you to, I guess you're going to have to use your calculator on this one, because that pi over 5 isn't one of our nice reference angles. Yeah. So this one you need to be in radians. So just sine of pi divided by 5, and then do sine inverse of that. We're getting 0.628. They want an exact answer. Okay, sorry about that. Yeah, I screwed that up. So, sorry. If you look on page 622, they kind of iron it out for you. So, basically, if you have the sine of sine inverse of x, that's going to be equal to x so long as x is in -1 to 1. Otherwise, you're having to do that method where you kind of have to do one step at a time. So if you have sine inverse on the outside and then sine of x, you have to evaluate this first, and then you'll have, you know, sine inverse of something, and then you figure that out based on the unit circle. Okay. So for cosine, the way that works, then it's kind of the same spiel. If cosine, if cosine inverse is on the inside, then it's just automatically x when x is in -1 to 1. And so if cosine inverse is on the outside, that's when you have to do it in pieces. Okay? So in that case, it'll be you figure out this part, in which case you'll have cosine inverse of something, and then then that'll equal something based on the unit circle, okay, where cosine's going from 0 to pi. And then for tangent, it's automatic. If you have tan inverse on the inside, it's just automatically going to be x. But if it's on the outside, then again, you're going to have to do that piece by piece kind of thing, where you evaluate tan of x, and then figure this part out on the unit circle from -pi over 2 to the pi over 2. Okay, so let's try it again. I apologize. I'm not perfect. Anyways, where did we kind of leave off? Is this? No, that's not one of them. This is just a calculator problem. Let's try a similar question. So we have sine on the outside and sine inverse on the inside. Sine on it. So this one, 0.2 is in this interval, so it's just automatically 0.2. Okay. Okay, so sine inverse is on the outside. So here we need to kind of do the piece by piece method. For this problem, because you have pi over 5 is in the first quadrant, it's just going to end up being pi over 5. Okay, so you'll kind of get this angle, the sine of 5 over pi, and then sine inverse of that is just going to give you pi over 5. Because it's in the first quadrant, okay? So if you go back and kind of look at what we were doing with regards to these kind of compositions, the first one we looked at, that pi over 3 was in the first quadrant, so they kind of had a natural cancellation, and you're just left with a pi over 3. And the second one, the 5 pi over 6, is not in that first quadrant. If it was sine of pi over 6, then sine inverse of sine of pi over 6 would just be pi over 6. Okay. This one, again, it's not in the first quadrant, 4 pi over 3. If it was cosine of pi over 3, then the answer would just be pi over 3. And then same for this one, and then that one's undefined. Okay. So maybe we should say that this is just automatically x will equal x if this angle x is in the first quadrant. And that'll be the same for the rest of these as well. So cosine inverse of cosine x will equal x if x is in the first quadrant. This is getting ridiculous. And then down here, this will just equal x if x is in the first quadrant. Otherwise, you're going to have to do the piece by piece. Okay, so I think now we kind of have this process. We could probably program it into a computer if we were so ambitious, but let's see if it works now for us. Okay, so this one, pi over 5 is definitely in the first quadrant, so we'll go pi over 5, and of course it's not going to let me do that, so push word symbol. And we should be able to get them all correct now using that algorithm. Okay, so where are we? Sine inverse. So 4 pi over 3 is not in the first quadrant, so I'm going to have to do this one in pieces, right? Okay, so let's take a look. Here is our kind of range for sine inverse. Sine of 4 pi over 3 is 1 pi over 3, 2 pi over 3, 4 pi over 3. Sine is definitely negative in that third quadrant. The reference angle, pi over 3, sine of pi over 3 would be root 3 over 2. So sine of pi over 3 is negative root 3 over 2. And then our angle is going to be the negative pi over 3 right here. Okay. These problems turn out to be a little more challenging than I thought. Pi over 3. Oh, crap. Yeah, I typed it in wrong, sorry. 3. Now it's really... okay, next. Tan of tan inverse of 2. So where's my tan inverse? Tan of tan inverse of 2. So that should just be equal to 2. Tan inverse of tan of 7 pi over 6. So 7 pi over 6 is in the third quadrant, so we're going to have to fool around with that. Okay. Tan inverse of tan of 7 pi over 6. So again, where is 7 pi over 6? That's 1, 2, 3, 4, 5, 6, 7 pi over 6. Okay, it's just one more than 6 pi over 6. Okay. So it's in the 1, 2, 3, third quadrant. It'll be positive there. So the reference angle is pi over 6. Tan of pi over 6 is going to be root 3 over 3. And tan's output, its range, is from negative pi over 2 to pi over 2. So in that range, we want the one in the first quadrant, which is going to just be pi over 6. Okay. Sine inverse of sine of 3 pi over 4. So this one we're going to have to play with the unit circle. It's not in the first quadrant. So sine inverse of sine of 3 pi over 4. So where is 3 pi over 4? Well, 1, 2, 3 pi over 4s are here. Our normal range for sine is from negative pi over 2 to pi over 2. Sine is positive in that quadrant. So sine inverse reference angle pi over 4. Sine of pi over 4 is root 2 over 2. It's positive. So we just want pi over 4. So it's either pi over 4 or negative pi over 4. It can't be negative pi over 4 because of that positive root 2 over 2 value. Okay. So it just be backslash pi over 4. And this is a composite, so let's try this one. Cosine of 3/5. let's make sure it works, right? So what are we doing? So cosine is in between 0 and pi. Just going to draw big here. It's positive in here, so it's definitely in the first quadrant. Cosine is what? It's adjacent over hypotenuse. So adjacent is 3, hypotenuse, this is 3, 4, 5 triangle. Tan of that is opposite over adjacent, so 4/3. And tan of sine inverse of -7/25. Okay, so sine is in that first and fourth quadrant. Just want to make it bigger. Seems like I was making them too small. It's negative, so it's going to be in that fourth quadrant. Okay. Sine is opposite, so this is a negative value going downwards over hypotenuse is 25, and then I think it's 24 is the other side. So tan of that angle, so Pythagorean theorem is just this triangle comes up 24, 25 to 7 enough that I remembered it. So if you don't remember it, you got to do Pythagorean theorem and solve for the third side. Okay, so tan then is opposite over adjacent. It seems to be working. Okay, sine of cosine inverse of -√2/2. Okay, so cosine inverse of -√2/2. So you're thinking in the unit circle. It's got to be in the second quadrant, and it'll be some version of pi over 4, right? So here's 1 pi over 4, 2 pi over 4, 3 pi over 4. So it's a sine of 3 pi over 4. Which will be √2/2, right? So pi over 4 is a reference angle, sine is positive, so √2/2. So that was different. /√2/2. It's always a good idea for teachers to kind of go through and do some of these homeworks. Hopefully if you become a teacher, you'll kind of watch out for your students like this. Not many things you can do in life. Alleviating other people's pain is definitely a good way to go through life. Try to find ways to help people, in my opinion. I guess my opinions do not reflect the opinions of Cuyahoga Community College. Okay, but okay, so let's take a look. What am I doing here? Sine inverse is going from -pi over 2 to pi over 2. We need to be in the fourth quadrant because we're dealing with a negative here. The reference angle for 1/2 is the pi over 6. So we need the -pi over 6. So we're looking at secant of -pi over 6. That'll be for cosine, right? So 1 all over √3/2, so 2 over √3, which would be 2 √3/3. Oh crap. Well, you gave it to me. It's very nice of them. Cosecant of cosine inverse of -√2/2. So cosine inverse again is from 0 to pi. We want the negative, so pi over 4 is kind of the reference angle for √2/2. So we want 1, 2, 3 pi over 4. So we got cosecant of 3 pi over 4. Cosecant is just 1 over sine. Sine is positive, so it has to be output positive, and it should just be √2. Okay. backslash square root 2. Geez, more of these. Cosine of, well, I think you get the idea. Well, okay, we can do this one. Just make sure there's nothing weird going on here. Cosine of tan inverse. Tan inverse is going from here to here. And you can think of this as ratio of sides of a right triangle. So drawing, whoops, I got to be in this quadrant, right? And of course I didn't give myself enough room. This is opposite over adjacent. So the opposite side has to be the negative, because it's going down, and then the adjacent, this will be 5, and this will be, whoops, can't be 3. Opposite, how about opposite over adjacent, right? Opposite over, what did I do wrong? Oh, so 3 squared plus 5 squared equals c squared. 9 plus 25 is 34. So c is root 34, really. Cosine then adjacent over hypotenuse. So 5 over root 34, and rationalize it. So should get 5 root 34 all over 34. That totally doesn't sound right, but whew, this looks like some sort of calculator problem. The movie theater has 28 feet high screen, so they give us a picture here. We're going to be doing applications in 4.8, so this will get us ready for that. Yeah, I'll just do this last one and then cut the video. So we have 8 foot right here, and then 28 feet in this interval. And then we have our theta is right here. Okay, and they're even telling us what theta is. So theta is tan inverse of 36 over x minus tan inverse of 8 over x. Looks intimidating, but I think all you have to do is plug in the numbers. A movie theater, blah, blah, blah. If you sit x feet away from the screen, your viewing angle theta is given as this. Yeah, so you just put in 5 for the first one. I don't think I'm going to do all of these. I'm just going to do the first one to make sure we're on the right track. You want to be in radians. Okay, so let's convert our mode back into radian mode, which is in radian mode. And what do we have? Tan inverse of 36 divided by 5 minus tan inverse of 8 divided by 5 is 3 decimals, 0.421. 0.421. Yay, so it's just a plug and chug. Nothing to be worried about. Okay, so we'll leave it at that. Thank you for watching, and thank you for your patience at the end. One thing about math is you're kind of looking for procedures, and then these procedures can be programmed in the computers, and you just let the computer do all the work, right? So if you find a nice procedure, which is kind of like what I was outlaying here for you in the end, I think we have a pretty good program now. It's not perfect, but hopefully it'll get the job done. Outlining those programs, that's very important in math. Trying to decide, what you need to do, and then writing it all out, and then putting it into a computer program. Yeah, good stuff. Okay, so thanks for watching. We'll see you next time.